Alright, welcome to the first lesson of Unit 9. We're going to begin looking at areas and volumes, and so today we're going to calculate the area between two curves using a definite integral. So let's go ahead and discover how to do this. Here's the problem. We're going to take it one step at a time. You'll complete each step, and then we'll take a look at it together, and then you'll complete the next one. So let f and g be defined as given here. Our goal is to find the area between f and g from an x value of -1 all the way to an x value of 2. So go ahead and copy down the graph as I have constructed it here and graph each function on this interval. Okay, so here are the graphs of f and g, and of course our hope is to be able to figure out this area that's in between the two curves, between these x values. So as we've normally done with all of our discovery situations, we're going to first think about how we can approximate the area between the two curves. So don't overthink this. Think of the simplest way that you might be able to approximate this area. And based on what we've done in the past, the first thing you should be thinking about is using rectangles. Right? What if we can use some rectangles that are pretty close to, but not exactly, the area between the curves for certain sections, and then we can add those areas of those rectangles together. In other words, just using Riemann sums. So there's a reason I'm not sketching out all of these rectangles. I'm sure you can envision them here, but I want to dive a little deeper. Let's really think about what makes up the dimensions of those rectangles so that we can try and come up with a way to actually compute this approximation. So here's what we're going to do first. Draw small rectangles to represent the approximate area between the curves at the points C sub 1 and C sub 2, as I've drawn those points there. Your goal is to write an expression involving the functions f and g that can be used to compute the height of each rectangle. So draw these rectangles. You don't have to make them too big or too small, just so you can see the rectangles, and your goal is, of course, an expression for the height of each rectangle. Okay, so here are the rectangles that I've drawn. Let's take a look here and see if we can identify how we could find the value of the height using the values of our functions f and g. Let's start with actually the height of this rectangle at C sub 2, because I think that's easier to see. You can see here clearly that I'm dictating the height of this rectangle using the value of f and the value of g at this point C sub 2. And so this height is simply f at C sub 2 minus g at C sub 2. That will give me this height here. Now, we might hesitate on this second rectangle because you'll notice that g has a negative value here. So think about what contributes to the height of this rectangle. There's this distance, which is the distance from f at C sub 1 to the x-axis. And I want to add to that height this distance, which is the distance from the x-axis to g at C sub 1. Well, what would happen if I were to compute f at C sub 1 minus g at C sub 1? Well, f of C sub 1 is positive, so this would be a positive value. And then we'd be subtracting g at C sub 1. But g at C sub 1 is negative. And when I subtract a negative, that means I'll actually be adding that value. So I'll have this value plus this value, and that is the height of this rectangle. So I can continue to use the same method I just previously used, which is now just applied at C sub 1. Okay, so now that I've got the heights under control, I want to quickly mention what we should use for our widths. What's going to determine the width of the rectangles that we use, of course, is the number of rectangles that we have. And what we can do is just say, okay, if we have n rectangles, we'll split our interval up into n pieces, and the resulting width of each rectangle, we can just use a delta x. And of course, we remember what delta x is. It's just the length of our interval divided by the number of intervals that we have. So now we have a grasp on the height, and we have a way of determining the base of each of these rectangles. Alright, so now we're ready to write a sum that will give us an approximation to the area between these two curves using n rectangles. I want you to write that sum now on your own. So here we have our sum. It's going to go from interval 1 to interval n, and for each of those intervals we want to take the area of that rectangle and add it to the previous rectangles. So we need an expression here for the area, and of course we can compute the height of each rectangle using f at c sub k, whatever k happens to be, minus g of c sub k. That's that point, just as we've shown here. And then we can multiply by the base, which is just delta x, which of course depends on n. So we can represent that as such. And notice that I've just labeled what represents the height and what represents the base. Alright, so this will give us an approximation, and now we want to take it one step further. What must happen for our approximation here to be exact? Well, we've seen this many times before. We need to have infinitely many rectangles where the bases become infinitely small, and that means that delta x needs to be getting closer to 0, or in other words that n needs to be approaching infinity. So we're going to take the limit, either one makes sense, the limit as n approaches infinity, or analogously you could say the limit as delta x approaches 0. And notice that this is exactly the definition of the definite integral. As n approaches infinity, delta x is going to approach dx, the infinitesimally small change in x. And since we're going to be looking at infinitely many subintervals, we're actually going to evaluate this expression at not just c sub k's, but at every single x value between negative, in this case, negative 1 and 2. And so what we have here is simply the definite integral. In this case, we have from negative 1 to 2 of f of x minus g of x, that's our height, dx. And it's important to remember that this is still an expression for the area. We're simply adding the areas at every single one of these points from negative 1 to 2, and these infinitely small areas are going to build up and become the area between the two curves. So still here we have the height times the base, and so you need to think of this expression in here as representing the area, and we're simply adding these areas from negative 1 to 2. Alright, so now using our integral expression, go ahead and find the area between f and g on this interval from negative 1 to 2. You can do this by hand, or you can use a calculator. And in doing so, you get a value of 12. If you didn't get this value, one thing that you might check is when you're subtracting g of x from f of x, you're subtracting all of g of x. So you need to have what would look like in your expression, it would look like minus x squared minus 1. And so you would need to actually, if you were doing this by hand or in your calculator, you need to make sure you have these parentheses here so you can distribute your negative in if you want, or, in order to do this by hand, or simply enter it into your calculator. So if that was your issue, hopefully you were able to get it worked out. Let's go ahead and write down now the definition for finding the area between two curves. Alright, so here's the definition. Go ahead and write this definition down, and then I'll say a few things about it. Alright, first thing I want to mention is what is meant visually by f of x greater than or equal to g of x. As we saw in the discovery problem, visually that means f is above g throughout the interval, and it could also be the case that they momentarily touch, but f has to be at least equal to or greater than g throughout the interval so that I can use f minus g to find the height. The last thing that I want to mention, which is super important, is always have an understanding of why this integral makes sense. What we're doing when we're integrating is taking an infinite sum. So we're adding up these infinitely small areas for every single point from A to B. So this expression in here has to represent the area of those rectangles, even though it's infinitely small. And what makes up area? Well, area is simply the height, which is this expression here, times the base, an infinitely small base that is, but base nonetheless, represented by dx. And so all together, when I multiply those together, this is simply an expression for the area. And so you cannot forget that, because there will be times where you will be dealing with a complex problem, and you just want to go back to the fact that the area between two curves is this infinite sum of these infinitely small areas, which is simply height times base. All right, here are a couple of helpful tips for going through and finding the area between two curves. The very first thing you want to do is you want to graph both functions, whether it's by hand or with your calculator. You want to make sure you do that so that you can tell the relative positions of the functions. You need to know which one is above the other so you can determine how to compute the height, obviously. So you can see I've done that here. Also, the graph will help you determine the interval or potentially multiple intervals of integration. We saw an example where we were given the interval and there wasn't much we had to do. But graphing the functions will, for some questions, which we'll see some examples of in a second, will be very key to determining the interval or intervals that you need to integrate over. Here are some tips that can be helpful in order to make sure you have the correct integral. You can shade the area you wish to find. That will help you visualize what it is that your integral should represent. And also you can draw that rectangle or rectangles just to make sure that you are using the right dimensions. And so you can expand, a rectangle like this, and you can say, okay, what is the height made up of? What is the base made up of? And as we see some more complex problems, this will be very helpful in determining what your integral should look like. All right, let's go ahead and do a couple of examples. So you want to find the area of the region between secant squared of x and sine of x from x equals 0 to pi over 4. Go ahead and execute the process, find the answer on your own, and then we'll take a look at the solution together. So you can certainly graph these on your calculator. Regardless, you will need to remember that secant is the reciprocal of cosine. So secant squared x is 1 over cosine squared x, and when you have it like this, you might as well just graph it by hand. It's good practice. Sine of x is easy to graph at 0. Sine of 0 is 0. Sine of pi over 4 is root 2 over 2. We know it looks like that. 1 over cosine squared, cosine of 0 is 1, so 1 squared is 1, so we have 1 over 1. And at pi over 4, we'll have cosine is root 2 over 2. So when you square that, you get 2 over 4, which is 1/2. So you have 1 divided by 1/2, and we know that that is 2. So you'll be up here at 2, and so you can draw your function like this. Obviously, looking at your calculator will guarantee for you that secant squared is above sine of x, but you can do that by hand as well. And we know our intervals of integration, so we're ready to write our integral and compute. And here is that integral. Notice that I've just drawn this quick little rectangle to remind myself of exactly what my height should be. So here's the height multiplied by the base. And I can actually evaluate this by hand pretty easily. Antiderivative of secant squared is tangent. Antiderivative of negative sine of x is cosine of x, evaluated at pi over 4, and at 0. At pi over 4, I get 1 plus root 2 over 2, and at 0, I get 0 plus 1. And so the 1's will cancel, and I'm left with root 2 over 2. Important to remember, this is an area, so this is in units squared. Very key to remember. All right, let's take a look at one more. All right, we want to find the region enclosed by the parabola and the line y equals x. Notice what's missing, no interval. So what we need to do is trust the process, graph both functions, and then I think you might have an idea of how you can find that interval. So we can graph these functions pretty easily by hand. I've just done so by plotting basic points at x equals 0, 1, 2, negative 1, and negative 2. And when we do so, we can pretty clearly see what the region enclosed by these two graphs are. That's going to be the area which is bounded by the two curves. And so that's going to be this area here. And now you'll notice when I can visualize this area where I need to integrate from. I need to go from where they intersect first to where they intersect second. And from graphing, I can see pretty clearly this is negative 1 and this is positive 2. But even if I hadn't done that, I can always graph both functions in my calculator and find those intersection points. Or I can do it by hand. Remember, I'm just asking myself, where does the blue curve, 2 minus x squared, equal the red curve, which is negative x? And so I can solve that. 2 minus x squared equals negative x. And when I solve that, I'm able to see that I get values of x equals -1, and x equals +2. So I can begin writing my integral for the area. I know that's going to be the integral from -1 to 2, and now I just need to determine what will be the height and what will be the base. Of course, we know the base is simply the infinitesimally small change in x, and the height is going to be the curve that's greater minus the curve that's lower. So that's going to be 2 minus x squared minus -x. So now feel free to integrate this. Do it by hand, just to get some practice. This one can be done, and you can check your work using your calculator, and then we'll take a look at the solution. And in doing so, the solution that you arrive at is 4.5 units squared, and here's the work that went along with it. What we really want to take away from this problem is that in the question stem, they're going to give you information. You're going to receive information about the area that you're trying to find, and it's not always going to be an interval. Oftentimes, you'll need to graph and visually determine where your interval is going to be, and then you might need to do some work to find those points, either by using your calculator to find where they intersect, or by setting them equal to each other and solving. So you might want to add that to your notes on the definition, because this is going to be very, very important. Little errors here will cost you big time. Let's do one more problem. Okay, so here we want to find the area of the region in the first quadrant bounded above by y equals square root of x and below by the x-axis and the line y equals x minus 2. Just so you know, there are a few different ways to actually find this, this area. So trust the process, graph both of the functions here, shade in the area you're trying to find, and be logical. What expression is going to get you the area that you seek? Okay, so here are the graphs of the two functions, but you got to be careful. We want to find the area of the region in the first quadrant. So while you might think, oh, just between the two curves, between 0 and 4, that's not at all what it says. We want only the area in the first quadrant that is bounded above by this function square root of x and below by the x-axis and the line y equals x minus 2. So if I'm shading in this area, I'll actually be shading it in like this. And when you do so, you'll notice that the area you seek is not simply the area between square root of x and the function x minus 2 all the way through. At some point, that does become the case, but for the first 2 units, from x equals 0 to x equals 2, we're simply finding the area beneath square root of x and above the x-axis. Of course, the x-axis is just the line y equals 0. And so the area that we seek up to the point x equals 2 is just the integral of square root of x from 0 to 2. And I'll go ahead and go over that in white now. And then continuing on past x equals 2, I can see that if I were to draw a rectangle and look at the height of those rectangles, it would be square root of x minus x minus 2. That would give me the height all the way from x equals 2 to where they intersect at x equals 4. And so there I'm going to have a separate integral that will compute this area that is still in yellow. So my area of the whole thing can be computed as follows, where I have to just be very careful that my limits are correct, and I can look at my shaded areas to make sure that the white area here is from 0 to 2, and then the gold area is from 2 to 4, and that my heights are appropriate for each of those areas. And then going ahead and computing, I can do this in my calculator, or I could do this by hand. And either way, you end up with 3 1/3 units squared. Now I mentioned there are a couple of other ways to do this, so let's take a look at another way where you simply are looking at the problem a little bit differently, and I think it actually makes it a little easier. Imagine that you continued on taking the area underneath the curve square root of x that is above the x-axis. Notice that you'd get too much area, but that the area that you would need to get rid of to have the area you seek is simply a triangle. And also, it is a triangle whose dimensions you know. This is the point 4, 2. And so the height of this triangle is 2, And the base of this triangle is 2, and so the area of this triangle is just 2 times 2 over 2. In other words, the area here is 2. So if I just found all the area underneath my curve, square root of x, that's above the x-axis, and then subtracted the area of this triangle here, I would end up with the exact area that I seek. So let's compute that, and we'll notice that it's a little easier on the computation. Notice, of course, that in doing so, I still get the correct answer, but that my work is a lot easier. I'm only computing one definite integral, it's a lot more simple, and then I'm just subtracting away an easy to compute area. The moral of this story is that when we're finding areas, there is often more than one way. In fact, there's another way we haven't even looked at. And your job is to know all of the different methods so that you can pick the one which, in that particular case, is going to be the most efficient. That way you'll save time and get more questions correct. At this point, go ahead and move on to the homework 9.01. If you're looking for one more example problem, you go to the book, page 399. Example number 3 is a good one to take a look at.